Good evening, class. Hope everyone is well. This is the part two to the confidence intervals for a population mean where sigma is known. I'm going to try to just kind of, wrap this in a bow real quick for you. So we looked at kind of this idea of, well, we have this population parameter, in this case the mean, and we are trying to get a hold of it, right? It's somewhere in the ether. We don't necessarily know it, but we want to come up with an idea of capturing it, almost like a net. Okay, so you want to think of these intervals almost like a net. We first started with what we called, get back to the slide, a point estimate, and this is like if you only could say one number as like your best guess for what the mean would be. It turns out X bar is that best guess. Where X bar is just add them all up, divide by how many there are. And you'll always be able to calculate this because this is all relying on samples being taken. Samples as in, you choose n number of things. You have n number of elements in your data set. And so you can always calculate X bar in this case. And so our best guess for mu, if we only had to just use one number, would be X bar. And so we kind of did some things with that. The main reason we use X bar is for confidence intervals. Very rarely do we actually just use X bar by itself, because unfortunately, unless you're exactly at mu, which very rarely would you actually be, it's not a very good estimate for this parameter. So, and also, we have no way of calculating what are the chances of being, or the probability of being, a little bit off versus really far off. We don't have a grasp of how far off X bar is from the actual mean. And that's why these interval estimates that we've talked about in part one are so important. So let's get back to calculating these confidence intervals. Let's see, if we get through our slides here. There we go. So there's a nice definition. A C confidence interval for the population mean mu. You take your point estimate X bar, so you'll always calculate this, and you subtract E, your standard error, for the lower bound of the confidence interval, and then your upper bound is X bar plus your standard error, where your standard error is that critical value you calculate based on your confidence times sigma over the square root of the size of the sample. And so in words, this is kind of where the direction you go in terms of trying to construct these confidence intervals for mu. And this is key here, the fact that sigma is known. If sigma is not known, things are going to change, and that's what the next section's over. First, you want to make sure that sigma is known. If it is, your life becomes a lot easier. Obviously, the more information you know, hopefully the math becomes a little bit easier, and that is the case here. You need sigma to be known. You need the sample to be random, because you don't want to introduce bias. And either the population, the original population, is normally distributed, or n is greater than or equal to 30. And this is just so the central limit theorem will take effect. Secondly, you want to find sample statistics n and X bar. So n is just the size of your sample. X bar uses n. It's the sum of the x's divided by n. You just add them all up, divide by n, things we've done for a while now. You want to find this critical value using your standard normal. We went over that. If you need to kind of remember a little refresher on that, go back to part one. Calculate the margin of error. And then this allows you to find this lower bound and upper bound for the confidence interval. So let's actually construct one. We're going to use the data in example 1 to construct a 95% confidence interval for the mean number of hours spent on required athletic activities by all student athletes in this conference. Okay, so we had already calculated this before. X bar was approximately 21.1. The thing was already, if I'm remembering correctly, it already came from a normal population. If it didn't, hopefully n was greater than or equal to 30. Regardless, the standard error is approximately 0.7. That's sigma over the square root of n. So you calculate your left endpoint of your confidence interval, which is right here, x bar minus e. And then you calculate the right endpoint of your confidence interval, kind of this upper bound, and that's x bar plus e. So really all you're calculating here is the mean, which we've known how to do this since the first of the semester. And then we have this standard error, but we've actually already calculated this before with sampling distributions. And then you have this, you kind of have this critical value showing up. But again, this all comes from stuff that we've done before with the z-table and the standard normal distribution. So everything should seem familiar. It's just kind of putting it all together here. And so we're able to calculate this confidence interval. Now, it's one thing to construct a confidence interval. It's another thing to interpret it correctly. And so again, we'll talk about that in a second. But here we have the confidence interval on the real number line. And so we kind of thrown our net, right? We kind of had this confidence that if our net is this big, we've caught the population parameter mu. And so this is kind of how you want to think about it, at least for this class here. So the way we interpret this is, with 95% confidence, you can say that the population mean number of hours spent on required athletic activities, so mu, is between 20.4 and 21.8 hours. Now, this isn't saying the probability of this thing being in here is 95%. That's not what's going on here. This idea of confidence. So here, in this example, you can use technology to construct these confidence intervals. I want you to learn it without it, though. I think it's more useful, and you'll end up understanding more out of it. I get afraid with using technology too much. You kind of lose the meaning of what's going on. So you can go through these slides if you want. That's up to you. And so here we have another example, just to kind of round it off. A college admissions director wishes to estimate the mean age of all students currently enrolled. In a random sample of 20 students, the mean age is found to be 22.9 years. From past studies, the standard deviation is known to be 1.5 years, and the population is normally distributed. That's key here. Okay, notice you should have alarms going off in your head when you saw this 20 as your sample size. That's not greater than or equal to 30, but if you read on, they say it's normally distributed. They're assuming it is, and so we can do this confidence interval, and we can construct it reliably. Construct a 90% confidence interval of the population mean age. Okay, so again, we need to know what x bar is. Here, x bar is 22.9. We know the sample size. Sigma is given, right? Your standard deviation is given. That's what this whole section is about. It's assuming standard deviation is given. And we have this critical value. Remember, this is calculated based on the confidence level. And kind of just use your standard normal and your standard normal table using z-scores to figure out what this value is. Again, just go back to part 1 if you're not sure how to calculate this. The margin of error at the 90% confidence level is that critical value times sigma over the square root of n. And so we calculate this to be 0.6. And so now we can take our mean, our point estimate for mu, and our standard error, and we can create this confidence interval. We do x bar minus the standard error, margin of error, forgive me, and then x bar plus the margin of error. And we get the upper bound for our confidence interval. And so here it is on the number line to kind of get an idea. We've cast our net for trying to catch the population parameter mu. And to interpret this, we say with 90% confidence, you can say that the mean age of all students is between 22.3 and 23.5. Again, this is not probability. You're not saying the probability of mu being in this interval is 90%. You're saying with 90% confidence, that's a whole different thing. Okay, so let's kind of talk about what a confidence interval means. mu is a fixed number. You don't know it, but it doesn't vary. It's something that's out in the ether, but it is something. It's only one thing. It's not going to change on you. And so because of that, it's either going to be in the confidence interval or it's not. So you don't say this again. There is a 90% probability that the actual mean is in the interval, regardless of the interval. That's not what's going on here. The best way to interpret this, kind of really the drawn out way, but the most meticulous way to say it is, if a large number of samples is collected and a confidence interval is created for each sample, approximately 90% of these intervals will contain mu. Okay, and so what the confidence level idea is saying is, if you were to construct more and more confidence intervals, right? I don't know, capital N number of them. It doesn't matter. As you construct more and more of these confidence intervals, what we're saying is 90% of these intervals will contain mu, while 10% of them won't. Okay. And so we use this to make assumptions, and we interpret them in such a way that it helps us make decisions. So again, if a large number of samples, so we keep taking more and more samples. Something to notice here also is, for each time you get a new sample, X bar will change. Okay, and so these intervals are going to jump around on the number line. And what we're saying here is, if we do this enough, if we calculate enough of these intervals, 90% of these intervals will contain mu. And so here's kind of a good idea here. Mu is kind of centered here, and you have all these intervals jumping around mu. And it seems like most of the time, notice mu is in this interval, mu is in this one, but mu is not in this one. Okay, this is one of these rare cases. Mu is in these and all of these. So there's only one of these intervals where mu is not in it. 1 out of the 10, so 10% of the time, mu is not in the interval. And this gets more and more accurate the more samples you take and the more confidence intervals you calculate. Okay, and so to try to wrap this up pretty quickly, really this is just a calculation. We won't really go into how to like why the calculation is the way it is. What we're really worried about is, can we calculate it? And yes, we can. It's not that bad. To figure out the minimum sample size needed to estimate the population mean mu. Now remember, we kind of have this this rule that it needs to be greater than or equal to 30, but that's, it depends on, it's kind of a case-by-case thing. Your confidence level, your margin of error, your standard deviation. So this gives you a way of getting a more precise number. But the number is n equals that critical value times the standard deviation. Again, the standard deviation is known here, divided by the margin of error, all squared. Okay. If n is not a whole number, that's a typo there, then round n up to the next whole number. Okay, if sigma is unknown, we can't really do this here. We kind of have to assume that we have at least 30 members, and we have to actually estimate S, and that opens up a whole different avenue that we'll have to look at in the next section. So if we look at a quick example here, go back into example 1. We're looking at how many student athletes must be included in the sample to be 95% confident that the sample mean is within half an hour of the population mean. And so we can calculate this. We have our confidence level of 0.95, our critical value of 1.96, our standard deviation that is known of 2.3, and our margin of error of 0.5. And you just plug in, just plug it in your calculator, and you'll get n needs to be 81.29. So we need at least 82 of these student athletes in order to calculate this interval accurately. So the researcher has 40 student athletes, so the sample needs to be needs 42 more members. Note that 82 is the minimum number of student athletes to include in the sample. Okay, and so that's the end of this section. I'll try to post tomorrow another video on the next section. Make sure you are being as diligent as possible in your homeworks. And if you have any questions, just shoot me an email. Have a good day.